Hello boys and girls, this is Daniel again, and this video has some new stuff for you. We'll learn about stack and tail recursion. Alright, so we've already got into the habit of creating new applications for each video, so that's what I'm going to do here. So again, right click on the lectures.part1 basics, new Scala class. I'll call this recursion. And I'm going to make this an object, hit OK, and then extends app. Alright, so I'm in presentation mode in IntelliJ, and without any further ado, I'm going to just write the little factorial function that we used in the previous video. So def factorial, which receives an int. You can just paste it in your code if you want, but I'm just going to write it real quick. So if n is less than or equal to 1, I'm just going to return 1. Otherwise, n times factorial of n minus 1. Okay, so simple enough. So this function is recursive, of course. Okay, now technical detail. In order to run a recursive function, the Java virtual machine, on top of which Scala runs, uses a call stack to keep partial results so that it can get back to computing the desired result. So each call of the recursive function uses what we call a stack frame. So let me show you something. Let me get this else branch to be a block, and then see if this is as a result. And I'm going to print something, and I'm going to print computing factorial of n. Okay, and a little dash. I first need factorial of, and in parentheses I'm going to put in n minus 1. I'm adding these print statements so that you can see how the recursive call is actually computed. Again, after the result, I'm going to print computed factorial of n, and at the end I'm just going to return result. Okay, so the else branch is a code block. So the value of the code block is this guy, which is n times factorial of n minus 1. But we do some more things in the meantime, such as printing things to the console. It won't affect our final result, but I just want to show you something. All right. So let's try to run factorial of 10. All right. So right click, run. So we have all these print statements in the console where it says computing factorial of 10 needs factorial of 9, factorial of 9 needs factorial of 8, and so on and so forth until factorial of 2 needs factorial of 1. So this is the entire stack frame that the JVM needs to compute our factorial of 10. And then after it figures out the base case, the call stack is then freed with the intermediate results. So it just computed factorial of 2, then it feeds factorial of 3, feeds factorial of 4, and so on and so forth until it feeds factorial of 10, finally with this desired result. All right, so let's minimize this so that we have more space to see the code. Now, the trouble with this approach is that the JVM, the Java virtual machine, keeps all the calls on its internal stack, which has limited memory. So if I try to print factorial of 5,000, this thing will not be so pretty. So let's run this. And we have our first crash. This is called, so I'm going to scroll this all the way to the top, and this will be our first stack overflow error. Stack overflow errors happen when the recursive depth is too big. So as you see, the recursive calls stopped around the number 534 from the number 5,000 originally. So basically, the JVM tried to call the recursive function roughly 4,500 times before the stack blew up with memory. So we have our first stack overflow error. All right, so this is bad, particularly since recently I told you that you should use recursion when you want to loop. Now, a legitimate question would be, okay, Daniel, but what if I do want to iterate 5,000 times? Can I only iterate roughly 4,500 times. Isn't that a limitation? Well, the answer is yes, it is, unless we write code in a smart way. Now, let me give you another definition of the factorial function above, and let us define a new concept. All right, so I'm going to define another factorial. I'm going to call it just like that, another factorial, which again receives an int as a parameter, and it returns an int, of course. And inside, I'm going to define an auxiliary function. I'm going to call this factorial helper. This receives an int as a parameter. I'm going to call this x, and another int as a parameter. I'm going to call this accumulator. The return type is also going to be an int, and the implementation of this one is going to be, so this is basically the instance of the factorial. If x is less than 1, which is the base case for the factorial as well, instead of returning 1, I'm going to return accumulator. Otherwise, I'm going to call fact helper with x minus 1, and the accumulator this time is going to be x times accumulator. At the end, I'm just going to call fact helper with n and the number 1 at the beginning. So this guy is another definition of factorial. It runs the same. This is really not obvious, so let me break it down for you. All right, so another factorial of 10. Let's say we compute another factorial of 10, and let us prove that it does the same thing as factorial of 10, which is the product of all numbers up to 10. 1 times 2 times 3 times so on until 10. All right, so another factorial of 10 is this guy, fact helper of 10 and 1. Of 10 and 1. I'm just going to copy fact helper because I'm going to use it a lot. All right, so fact helper of 10 and 1. What is fact helper of 10 and 1? Is 10 less than or equal to 1? Well, no. Well, we're going to go on the else branch, which means that this is fact helper of 10 minus 1, which is 9, and 10 times the accumulator. Well, the accumulator was 1, so 10 times 1. Okay, now fact helper of 9 and 10. Again, is 9 less than or equal to 1? No, so we're going to go on the else branch again, which is fact helper. This time, x minus 1 is 8 because the original parameter was 9, and the accumulator is 10 times 1. And x is equal to 9. So this guy will be 9 times 10 times 1. Again, is 8 less than or equal to 1? Well, no. So we'll go on the else branch, and the parameter this time will be 7, and the accumulator will be 8 times 9 times 10 times 1. Again, going through the code, 7 is not less than or equal to 1, so fact helper will again be called recursively, and so on and so forth until we'll get to fact helper of 2, and the accumulator is going to be 3 times 4 times and so on and so forth times 10 times 1. Now 2 is not less than or equal to 1, so we'll get one final recursive call with x minus 1, which is this time 1, and then 2 times 3 times 4 times 10 times 1. Now I'm just going to rearrange this a little bit so that it's easy to see. So I'm going to put this 1 at the beginning so that it looks prettier. Okay, and at this last call, fact helper of 1 and the accumulator is going to go on the if branch because 1 is less than or equal to 1, so it's going to return accumulator. So this guy will return the accumulator, which is 1 times 2 times 3 times 4 times 10, which is the definition of the factorial. So fact helper here actually implements the factorial definition. Now, besides being a little fancier way of computing the factorial, the most interesting thing is that this way of writing the recursive function actually works with a big number. So if I call another factorial of 5,000, you'll be surprised to see that it works. Oh, but until then, let's comment out this little thing which crashes our program before. So let's right click and run again. Okay, so this thing actually runs. We didn't print out a number. Let's do that. We're probably gonna run out of integer representation, so that's why we see 0 here, because the number for 5,000 is absolutely astronomical and it overflows the integer representation. At some point it will be 0, so everything multiplied after that will turn to 0. We'll solve this problem. Let's use big int instead of int, and just replace the accumulators and the return types with big int, and right click and run again, just to see that this number is actually legit. So this is the actual number, which is the factorial of 5,000. A pretty big number if you ask me. All right. So the thing is that this another factorial actually works with big numbers. It works with 5,000. It works with 20,000 if available. So it'll probably take a second or two, but we have a legit number with factorial of 20,000. Okay, so the question is, why doesn't this guy crash with a Stack Overflow, even though fact helper is also recursive? Don't let the fact that I put it as an auxiliary function fool you. It doesn't really matter. Okay, so I can actually call fact helper on its own with 20,000 and it would still run fine. In fact, let me try that. So don't try this on your code. I'm just gonna prove this to you. And I run fact helper with 20,000 and 1, and just print this out and comment the another factorial thing. You'll see that the fact helper can actually run on its own. Okay, so this ginormous number is the result of fact helper. So the fact that I put it as an auxiliary function doesn't actually help. I'm going to undo my modifications. Okay. Right, so the question is, why does another factorial work and why doesn't the first one work? The trick here is that we wrote fact helper right over here as the last expression of its code path. This allows Scala to preserve the same stack frame and not use additional stack frames for recursive calls. In the previous implementation, Scala needed a recursive call stack frame for each recursive call, so that it computes the intermediate result so that it can then multiply it with a number and then pass it back from the stack. But here, it doesn't need to. The Scala doesn't need to save intermediate results to be used later, so when you evaluate this recursive call, the current stack frame, for example, fact helper of 10, is replaced with fact helper of something else without using extra stack memory. This is called, I'm going to write this in all caps, this is called tail recursion. And IntelliJ is smart enough to figure out that this method fact helper is tail recursive. This guy is not tail recursive because the factorial recursive call does not occur as its last expression. So the key ingredient of tail recursion is to use a recursive call as the last expression on each code path that it occurs. If you're not sure if your functions are tail recursive, you can add a tiny annotation before the function definition. You can add tailrec, and this guy will tell the compiler that this function is supposed to be tail recursive. If the function is not tail recursive, then the compiler will issue an error for you. So if I add this annotation with the previous factorial function, then the compiler will complain because it says recursive call not in tail position. That is, it's not the last expression of its code path. All right, so the tailrec annotation will not work. From now on, we'll try to make our recursive methods tail recursive because that's how we can actually achieve the iteration versus recursion approach that we talked about in the previous videos. So the answer to the legitimate question of, Daniel, how do I iterate when recursion is limited, is a more complete when you need loops, use tail recursion. All right, so a pretty important topic, people, which requires some exercises. All right, so I want you to write the string concatenation function from the previous video. So the function that concatenates a string n times using tail recursion. Then I want you to create an isPrime function, which is tail recursive. And 3, I want you to create a Fibonacci function, which is tail recursive. Any function can be turned into a tail recursive function. The trick here is to use these little accumulators to store intermediate results rather than call the function recursively. You need as many accumulators as you have recursive calls on your code path. Sometimes you need more than one accumulators. This is a hint. So pause the video now and think about how to solve these 3 functions. Well, let's start with concatenate tail recursive. So I'm going to define concatenate tailrec, which takes a string as a parameter, the number n as a parameter, and an accumulator, which is a string, because accumulators need to have the same return type as the intended return type for the function. This finally returns string, and the implementation is going to be something like, if n is less than or equal to 0, then instead of returning the base case, which is the empty string, I'm just going to return the accumulator. Otherwise, I'm going to call concatenate tailrec with the same string as a parameter, with n-1 this time, and the accumulator will store the concatenation between a string and the old accumulator. All right, so take a couple of seconds to process this. If I print line concatenate tailrec with the string hello and the number 3, which is the case that we used in the previous non-tail recursive function, and of course the accumulator will start with an empty string, we'll see hello, hello, hello printed 3 times. Okay, so hello, hello, hello. So the concatenate tailrec actually works, and to make sure that our function is tail recursive, let's add the tail recursive annotation. So this function is good. Good. Now for isPrime, which takes a number n, which is an int, and this returns a boolean. And I'm going to define an auxiliary function inside, and that will be tail recursive. So def isPrime tailrec. Right? This will take the same parameter t that we used in the previous video, but instead of calling the isPrime until function recursively, I'm going to store the result as a boolean as an accumulator, and I'm going to call this isStillPrime. Okay, and the final return type will be a boolean, and we'll use the same base case, which is if t is less than or equal to 1, we're just going to return true. Okay, now slight modifications. If isStillPrime is false, there's no point in calling isPrime tailrec recursively, because n, the number that we originally started with, is not prime. So if not isStillPrime, then we're just going to return false. Otherwise, if t is less than or equal to 1, we'll return true. Otherwise, we're going to call isPrime tailrec recursively, isPrime tailrec. And the number t, which was the limit, is going to be t-1 this time. And the accumulator will store the fact that n mod t is not equal to 0. So remember, this expression was in the previous implementation outside of a recursive call. Now it's inside, and it's stored in the accumulator. And the old value of the accumulator is still prime. Okay, and the main implementation of is prime is going to call is prime tail rec with t. Again, the limit is the half of n, and is still prime will start with a positive assumption, which is true. All right, so if we call is prime of 2003, that should return true, and print line of is prime of, if I remember correctly, 629, that should return false. So let's right click and run this. So 2003 is a prime number and 629 is not. So this function works well, and let's add the @tailrec annotation for the auxiliary function just to prove that we took the right approach, and it's done. This function was not simple, so take a couple of seconds to actually process this. Is still prime basically holds the intermediate result, so instead of calling the function recursively with n mod t naught equals 0 and the recursive call of is prime until, we store that in the accumulator. All right. Okay, and finally, we have the Fibonacci number with n as an int, and this returns an int. And I'm going to use an auxiliary function here as well. This function is also not trivial, and it has a little trick. So Fibo tailrec. And this will take 3 parameters. This will take the ith number that I want to compute. Okay. And then instead of 1 accumulator, we'll use 2 accumulators. That is because Fibonacci calls Fibonacci of n-1 and Fibonacci of n-2 in the same code path. So a general rule of thumb is however many recursive calls you have on the same code path, that's how many accumulators you need to have in the tail recursive function version of the function that you want to implement. All right, so we have 2 accumulators to store. We're going to call this last, which is an int, and next to last, which is the previous Fibonacci number. So this is basically Fibonacci of n-1, and this is Fibonacci of n-2. That's the results that we're going to store in these accumulators. Of course, we'll return int, and the implementation is going to be, well, if I is bigger than or equal to n, so we'll start from I equals 2. And if I grows bigger than n, then I'm going to return the last number because that's the final result that I care about. Otherwise, I'm going to call Fibo tailrec with I plus 1, so that's the next number. And the accumulators are going to be, the last number is going to be the sum of these two, because that's the property of the Fibonacci stream of numbers. So last plus next to last. And the previous Fibonacci number is going to be the last number. Okay, and as the main implementation of the Fibonacci function, I'm going to put in an if expression just to optimize. So if n is less than or equal to 2, I'm just going to return 1. Otherwise, Fibo tailrec with 3. So this is the starting index for the Fibonacci tailrec call, and the accumulators are 1 and 1 because these are the two first Fibonacci numbers. So if I print line Fibonacci of 8, I should see the number 21 if I remember correctly. Oh, I see the number 13. Well, why is that? Well, I have 1, 1, 2, 3, 5, 8, and 13. So that is the 7th number. Oh, silly. I did say I was going to start from 2, right? So if I run this again with the number 2, yes, I'm going to get 21, which is the number I care about. All right, this was also a tricky question. You needed to figure out that you needed 2 accumulators instead of 1. These are hard exercises, and this gives you a taste of what functional programming is about. But don't worry, I'll guide you along the way, and these practice exercises will work miracles as you progress through the course. Alright, quite an important topic today. Make sure you get this right because it will prove very, very useful as you progress in your Scala journey. I'm Daniel, and I'll be waiting for you in the next video.